So, I'd like to interrupt our regularly scheduled lecture. I should show one of those little TV test patterns or something. To remind you that Earth science can be a current event, is current events. Most of you are probably aware a couple weeks ago there was a huge earthquake in Turkey. We didn't talk about it when it happened because that was the week everything went crazy for me. And I knew we'd get to earthquakes eventually, and I would just mention it then. Well, I don't know if you heard, but they had another one yesterday. 6.4 or something. We'll pull up the actual numbers here in a bit. The one that happened a couple weeks ago was devastating. I don't usually like to focus with any natural disaster. I don't like to highlight the horrible bits of it. But I think at last count they were up in over 46,000 dead, which is just mind-blowing, horrific. There was only a couple hundred injured by this most recent one. Perhaps because everything that fell was going to fall, or that fell last time. It may have been. I didn't look and see if it's in the same exact district, area. So that might be part of the issue as well. So whenever something like this happens, if a volcano on the west coast might decide to erupt, I would interrupt our lecture and talk about that. Okay. If a hurricane hit, and we hadn't already talked about that during the semester, we would stop and talk about that. So today, we're going to talk about earthquakes. It's worth noting, and this is what I was just grumbling to myself, digging through my emails here a couple minutes ago, when Turkey had the big one 2 weeks ago, there was actually an earthquake in Buffalo. Same day. It wasn't huge. I wish I could find the article. Like I said, the email is blank. I don't know if the article expired. I don't know if that works, but we'll talk about small local earthquakes here in New York when we get there. But yeah, that was kind of weird. So earthquakes, and I'd like you. I know it's been up for a couple minutes, but I want to point it out now. I want you to take a moment to appreciate how difficult it was for me to italicize every other letter to make it look, like it's shaking. No? Yeah. I thought it was cool. But So what is an earthquake? Well, a sudden trembling of the earth caused by the release of accumulated energy in rocks. You got the sudden trembling part, I'm sure. Who doesn't, right? We're going to try to explain to you how energy can accumulate in rocks, why, and then the releasing bit as well. Okay? Whenever they talk about earthquakes, they use the word seismic. In fact, one of my most favorite earthquake questions it's a sentence. You've got seismic energy, seismic waves, seismograph, which you've probably seen in the movies. That's the little red pen bouncing on the on the paper, I mean. You've got a seismogram, which is what comes out of the seismograph, and you've got the seismologist. They use the heck out of size. So I have like 5 sentences, and one of them makes sense. So you could look forward to that on the next test. So anytime you see seismic, they're talking about some sort of geophysics, some sort of internal earth energy stuff. All right. Generally speaking, earthquakes are caused by one of two things. They're caused by plate movement, as in plate tectonics, okay? Or it's caused by settling. Now, this semester, we haven't talked about earthquakes or volcanoes yet. To you folks at home, if some semester that I happen to be reusing this thing, if we've already talked about volcanoes, you might have heard this. Generally speaking, nearly 3/4 of the world's earthquakes and volcanoes occur along what we call plate boundaries. Okay, plates are these giant hunks of the Earth's surface, essentially, for lack of adding more vocabulary words at the moment. And you know that they're moving around the surface of the Earth in a variety of directions and a variety of speeds. I trust that you learned that in high school. All right. Well, where they meet two plates, we call it a plate boundary. And that is where, as I said, the majority of the world's earthquakes and volcanoes occur. There are, however, like New York State, for example, some areas that are nowhere near plate boundaries, where we still see the occasional odd earthquake. And that's due to a really vague general term here, settling. We had one, I'm going to say 10, 15 years ago around here, and one of my old students had gone on to work for WIBX, I think it was, and they called me to do an interview on the phone for the radio, and I was like, oh my gosh. Every one of the, I think it was Andy Warhol says you get your 15 seconds of fame. I think he said 15 minutes. I got 15 seconds. So my big sound bite was that the Earth is old. She's like an old house, and every so often it settles and it rumbles, something like that. And that's exactly what we're looking at here. There's no plate boundaries, but there are ancient seams from when this continent was put together. All right, and for any odd number of reasons, and sometimes no visible reason, it just kind of creaks and groans and settles, and that reverberates at the surface. But the majority of the ones you hear about, Turkey, San Francisco, anything over on the east coast of Asia, Japan and over there, that's plate boundary stuff, the big stuff that really does some damage. So we kind of just talked about this, really. I got ahead of my slides. That ring of fire there, that is that nearly 3/4 of the Earth's surface. That is basically the rim of the Pacific Ocean. Starting with us, it goes down the west coast of North America, the west coast of South America, circles around above Antarctica, and comes up through the middle of the Pacific over what you would call the Pacific Islands, and then up the coast of Asia. It actually goes across the top, too. Many of you know that between Russia and Alaska up there isn't too horribly far away. We've got a chain of islands up there called the Aleutian Islands. They're there because of all of this as well. So that's the ring of fire. It could also happen in the middle of an ocean. It could happen in the middle of a continent. All right? We have plate boundaries in a number of different scenarios or locations, however you want to say it. And then, as I mentioned, I didn't use the word stable continental interior, but I mentioned these places where we don't have active plate boundaries. What the word there is a fault. And a fault is nothing more than a break in the rock. Believe it or not, faults get an entire chapter. I always skip it. In geology and earth science and wherever. My goodness, they go on about all the different ways that rocks could break. And at this level, you just need to know that rocks are old. They are broken. Okay? And that they call those, again, faults. So essentially, earthquakes can happen anywhere, but they're much more likely to occur around these plate boundaries. This is a map that shows essentially the plate boundary. It shows a lot of stuff, but those big sort of marks that look like stitches, the black lines going all around it. All right? Those are the plate boundaries. The areas in between are the plates, so solid rock. And yes, solid rock is under the ocean. That's the ocean floor, the Pacific Ocean, of course. All right. Down the middle of the Atlantic. Scooch over to the other side of North America. It takes a moment to find us on here because you're used to North Americano-centric maps where we're like right there. We're kind of off to the side in this one. But there's a big suture right down the middle of the Atlantic Ocean. So the plate that we live on starts there in the middle of the Atlantic and goes all the way to the west coast of North America where the Pacific plate kicks in. So on either side, you've got that plate boundary we were talking about, okay? And you see there's a whole bunch of other plate boundaries all over the place. There's like 7 big plates and a dozen or so little ones. And if you look at this, you might see that they kind of go through right where we tend to have the issues. All right. So a couple more just generic earthquakey words that you need to know. Epicenter, you hear that a lot. Okay? Epicenter you hear about because that's going to be your town name, your city name. That's the location at the surface of the earth where they felt the damage, where they felt the earthquake. The focus, on the other hand, is where it actually happened. They will tell you an earthquake occurred at a depth of 300 meters below, what's the place up north that gets a lot? Messina, New York. Messina gets a lot of earthquakes. So that's the focus, where it actually happened. Epicenter, again, is somewhere you'd know. So they're actually telling you both when they say depth of 300 meters below Messina. They're giving you the focus and the epicenter. I will put these PowerPoints up, by the way. Again, I hadn't planned on giving this lecture today, so they're not posted yet. Just an example, or an illustration, I should say. And that black line diagonal, that would be a fault. Or a plate boundary, depending on your situation. But this one, I just know it's a fault. It's where the slippage occurs. The rocks moving. That is the earthquake. So here's that seismic word again. All right. Like I said, earthquake energy is always referred to as seismic energy. It's a whole lot like sound waves. If you can picture sound waves traveling, you can picture earthquake waves traveling. We've all seen, I think it's some sort of oscillator, I forget what the heck it's called, but that thing where you talk into it and the lines jump up and down, and the louder the baby cries, bless you, the bigger the lines get, and it's a measurement of the sound waves. They like to have them in the science museums. And maybe you've seen them when they're trying to recognize somebody's voice pattern recognition. There's a handful of ways they show you this. But sound travels as waves, okay? And the seismic energy travels as waves. We are going to recognize 3 of those waves. We're going to talk about P waves, S waves, and I say Raleigh waves. It may be pronounced Rayleigh. For some reason, I started saying Raleigh 25 years ago, and it's stuck with me. But it's probably Rayleigh or Rayleigh. Now, this energy can travel essentially 2 places. Through the earth and then released at the surface of the earth. All right? When we're talking about energy traveling through the earth, that's body waves. And those are the first two from that previous slide, the P and the S wave. When this energy works its way to the surface, that is, thank goodness, called a surface wave. That's the Rayleigh wave. Spoiler alert. The P waves and the S waves are a little different, and what happens when they get to the surface, they mix together. And that's when they cause a whole bunch of havoc. So body waves and surface waves is the point of this slide. Now we've got a couple video illustration-y things to show you in a minute if you don't quite get what we mean. All right, so don't worry yet. So a P wave stands for primary wave. All right, and they call it that because it travels faster than the other wave, and therefore is the first one to hit the seismograph. All right, so it's the first one that hits the recording device. Now, it says that it is compressional, and that what compressional means is that energy travels parallel to the wave direction, essentially the same way as the wave direction. And that's what I said. Don't worry, we've got a video in a second. Lastly, P waves are transmitted through solids and liquids. Read that as solid and molten, because we're going to think the middle of the earth is composed of molten rock. You wouldn't really think of it as liquid rock, but I want you to understand that that's what we're getting at here. So P waves travel fastest, arrive firstest. The energy travels parallel to the wave direction, and it's transmitted through solids and liquids. Like 3 things to know there. Okay? Okay. S waves, on the other hand, secondary. All right, they arrive second. They travel slower. That's why they arrive second. These guys travel perpendicular to wave direction. Perpendicular means at right angles, right? So, and lastly, these guys are only transmitted through solids. We'll take a quick peek in our magical cabinet over here and see if we have a slinky left over here. For this high-tech stuff, we need high-tech tools like slinkies. Have you guys seen a slinky in here? You've been all through here more than I have. I don't think so. Anybody remember seeing a slinky? Well, luckily we have a video of somebody playing with a slinky. But I always like to show you if you can. You need a classroom slinky. So this is not a great diagram to show you what we're talking about. The P wave, compressional. What you want to look at is right here where it gets narrower, right here where it gets narrower, right here it gets narrower. It kind of cycles, all right? You'll see it in the slinky, but I just want to show you what you're looking for. The S wave, this is easy. This is crack the whip, all right? You shake a rope that goes this way, it's going to go like an S, up and down, S up and down. This is what we mean by perpendicular. This is an easy one. All right. So when an S wave is going through the rock, it's going like this, up and down, up and down, up and down. The P wave is the toughie. Let's see if this link actually works. There's no sound to it. It's just... and it's unfortunately really short. Where's the loop button, you guys? All you YouTube heads. Right here? No. Pause button. I totally missed it because it's not playing anymore. Replay. I thought there was a loop.
The autoplay button? Autoplay is next video.
Yeah, you used to be able to loop it.
Yeah, I don't think you can.
Well, let's do this. Let's at least slow it down. Maybe I'll do screen capture one of these days and I'll loop it myself. All right, so up top you see the S wave, all right? And that's the going up and down. We talked about that, fairly simple. I will replay this in a minute. You see that thick spot that just went off the screen. It condenses and moves, but behind it, it gets narrow, it gets wide again. So you could actually do this. I thought I had a picture of a guy actually pushing a slinky. If you have a slinky at home, or you guys are starting to work in schools, they might have the slinkies there. Take it and sit at a desk and stretch it out about arm's length from it with you. And give one side a quick shake like this on the table. And you'll see it move through that way. It's kind of neat. And maybe the next slide is somebody doing that, but I don't know. I thought it was this one. No, sorry. So you have to play with your own slinky. If I think about it Friday, I'll grab one from upstairs. But pretty simple. And like I said, just give it a quick jerk with one hand, and you'll see it zip through. And it's compressional because it's squeezing those coils together in the slinky. So, as I said, at some point, those energy waves are going to reach the surface. So seismic energy is going to reach the surface. And that up and down motion and that squeezing together motion are going to mix. And it's just going to shake the heck out of everything at the surface. All right. These are surface waves. And also because they're running into one another, the waves are like colliding, it slows it down, which is even worse because the shaking then lasts longer. It might have zipped through the rock before, but then once it hits the surface, everything's bouncing off of everything else. Reverberates, for lack of a better word. You see ground roll in here. They like to show, Hollywood likes to show suspension bridges during an earthquake. Okay, and they kind of do that S-wave pattern as well. The ground can literally do that where it just kind of rolls going along with the energy. It's moving forward, that's your compressional energy, and it's also moving up and down. That's your other energy. We have to assume there was a Professor Rayleigh at some point that realized this, and that's why we called him that. Because, you know, P waves and S waves were too simple, so we had to attach somebody's name to this one. But, hey, if we discovered something, we'd want our names on it too, right? I don't think this is animated. If it was, it won't play anymore. So this kind of tries to show how the Rayleigh waves move forward and up and down. Basically what we've been saying. All right, measuring seismic energy. Speaking of naming stuff after people, is Mr. Richter and Mr. Mercalli. Okay. Mercalli was first. It's very old. And what we're going to see here is two words you may have be used to comparing. I suppose they rear their ugly heads in education as well. Qualitative versus quantitative. All right. When you guys are teachers, qualitative, you're going to use a bunch of adjectives to describe maybe your student. Good terms, bad terms, whatever. Quantitative is, boy, that score at the end of the year. A 93, a 73. Okay, that's the difference between quantitative, quantity, and qualitative, a quality. All right. So the Mercalli is qualitative. I'm going to show you one in a moment. It shows a whole list of things that happen at certain levels. The house shakes, the dishes rattle, but nothing falls or breaks. Well, the next step up might be all of that plus stuff breaks, including your windows. And the next next level might be the house crumbles. And so on. It describes things. Okay? The Richter scale, on the other hand, is quantitative. It is a number, a 5.7, a 6.3. You hear these numbers all the time. And this is made, or this is recorded by that seismograph that we talked about. And the cool thing about this is, you know how scientists are, right? They love to not just get numbers and data on stuff, but they want it to be comparable. So the idea here is that as long as you keep your seismograph maintenance up to date, just taken care of, a 6.3 in India means the same thing as a 6.3 in California and a 6.3 in Japan. It's the same amount of energy every time. That we can work with. Because if you think about the bottom option here, Mercalli, that relies on a lot of external things. How well the houses were built, for example. What kind of material they were built on, sand versus solid rock, and so on and so forth. It's not comparable. Because you could be talking about a village full of huts versus skyscrapers. And the same thing that levels the huts is not going to level the skyscrapers. So there was a point in time when it was probably more useful than it is. All right? But it's not great. And the other problem is it relies on humans. And we're horribly unreliable. I remember the Buffalo thing and the Buffalo earthquake, reading about it. And one gentleman said that it sounded like a truck ran into his house. Okay, he must have been maybe very, very close to the fault that slipped. But if you go and ask his neighbor, and let's say, he's like, oh my gosh, I'm on the news. I don't want to be a big scaredy pants. And he was like, no, I didn't notice anything. It was fine. I slept right through it. And where he could have been hiding in his closet, you don't know. Okay? And it's not even necessarily based on our behaviors or our thoughts or our concerns. The one we had in the Utica, Rome area, I wish I remember where it was. But the one like 15 years ago I told you about, I was teaching in Rome when it happened. And we were in a classroom very much like this one. 2 doors down, the lab manager, she was in her office. Her office is also the chemistry supply room, so it's full of glass beakers, test tubes, whatever. So I'm sitting there talking. You guys know I'm loud. You can hear me, especially folks in the front row here. So I'm just lecturing along, doing this, doing that. And all of a sudden she comes running down. Oh my gosh, are you guys okay? And we're kind of looking at her like, yeah, why? Well, her room rattled like crazy. And here we thought maybe, again, we didn't even think about it, maybe a truck drove by, didn't pay any mind to it. All right. But you've got that machine in the basement screwed into the bedrock called a seismograph. Whether you were in her room, whether you were in our room, it's a 3.1 or it's a 2.7. It is what it is. So that's why we really, we like to use that Richter scale. It allows research to go on. It allows us to be, comparative. Because there's big money in building earthquake-proof buildings and engineering and architecture. Oh my gosh, think of these cities, okay, these major cities that fall along these earthquake zones. And they're tired of rebuilding, let alone the loss of life. So they want to be able to have data behind what they're doing. Questions about that? Because like I said, these words, quantitative, qualitative, I didn't use the objective and the subjective, but I think at this point you kind of get what they mean. Questions about that? Cool. All right, so this is really hard for you to read, but some actual examples of what's in here. Level 1, Mercalli, only felt by sensitive instruments, whatever those may be. 2 is a little better. Felt by few persons at rest, especially on upper floors. Delicate suspended objects may swing. So you see where we're going with this, all right? We'll jump up a couple. 6. It goes up to 12, so we'll look at 6. 6 is felt by all, falling plaster in chimneys, light damage, but some fear. That's not very measurable. 12. 12, unfortunately, is measurable. Total damage. Can see the earthquake wave move through the ground. Gravity overcome. Objects thrown into the air. That's bad. So, what was the one I read? I didn't read this one, but let's do 3 here. Felt indoors. Not recognizable as an earthquake. Maybe a large passing truck. Okay, we talked about that in Rome just now. That equals a 2.5-ish. The level 6 is a 4.5. And then upwards of the 11 and the 12, that's an 8. All right. Richter scale. Well, let me make sure there's not a slide before I say it. Yeah, there are some 9s. Say Richter scale, I think goes up to 10. We've ever only gotten to 9. And even this is relative, okay? It's all based on wave height. Again, remember that red pen bouncing on the piece of paper? All right? It's a measure of how high that red line bounces above the center line, which is just background noise. So these numbers we come up with, this 2, 3, 4, 5, 6, 7, those in and of themselves don't mean anything, but they relate to energy levels that push that pen up. Okay? So in that sense, that's how they mean something. The other thing, and that's that amplitude or height. Okay? Right here, the second bullet. That's that red pen bouncing up and down. The other thing that's important is this logarithmic increase. You guys might remember semi-log graph paper or log graph paper. You may know what it was. You may not have ever known what it meant, but you had to use it. The idea was that it wasn't even, right? That's the deal. So what we're doing here with this logarithmic increase is every time you go up from a 3 to a 4 or a 5 to a 6, it's a 10 times increase in power. 10, 100, 1,000, 10,000. So moving from a 4 to a 5 is a really big deal. Moving from a 6 to a 7 is a really big deal. Because there's a 10 times difference in energy release there. It's not just going from like an 80 to a 9, well, 80 to a 90 on one of your tests. It is kind of the same. But, no, because the first jump would be 10 to 100. Yeah, so it's not like going from 80 to 90 on your test. It's 10 times that even. All right, so 10 times the magnitude, 30 times the increase in energy. I think I said energy. I apologize. It's 30 times the energy at each jump. So the largest ones we've recorded since we've been taking care of our seismographs, installing them all over the world. we've got some biggies, some 9s. How old were you guys in 2004? 1. 3. Yeah. All right, either way, you didn't remember this. You guys might remember the Sumatra one. It was Christmas day after Christmas. I'm not sure if they're Christian or not in Sumatra, but it was a horrible Christmas gift. Sumatra is an island in the Pacific, probably not too horribly high above sea level. They had a huge earthquake offshore and a tsunami, which I haven't officially introduced that word yet, but you guys know a tsunami is a giant ocean wave, probably. Just wiped the island off it was horrific. I don't know that they hit the hundreds of thousands. They don't have that many people living in Sumatra, probably. But anyone at the coastline, it was just devastating. And it happened really early morning, one of those things, everybody's still asleep. I think that's when I first started doing this lecture as current event sort of thing. Well, we wouldn't have been teaching at Christmas, but it's somewhere thereabouts. Somewhere thereabouts. So we've been talking all about this energy. We don't really talk about how it got there. So what this says kind of goes towards addressing that. I'm going to go off slide for a minute here, and I'll use one of these pencils. One that's, well, he's even got all good pencils in here. Well, I'll try not to hurt it. So this pencil is a system. A set of rock is a system. It's just whatever body we're talking about, right? And by putting force or energy into the system on either end of it, it's starting to bow, all right? And you know, if you were closer, you could probably hear it starting to snap and crack. And if I let go, it's okay. These are really strong pencils. If, however, I keep doing it, I don't want to hurt anybody, I push it far enough, it's like 6 little dings over there. I put in at some point more energy than this system could take, okay, and it broke. So what this slide is talking about is how much energy any given system can take is kind of dependent on a couple factors, rock type being one of them. And God forbid some places that are even on sediment. All right. But generally speaking, they talk about the type of rocks. Some rocks are more durable than others. They can absorb more energy. You guys may or may not know your rock names yet, but say igneous rock, something that used to be magma or lava, can hold a lot of energy. It's a solid, cohesive rock. All right. Something on the other end of the spectrum, like a sedimentary rock, which is pieces, parts glued together. It's particle board, really. That cannot hold as much energy. All right, and that'll break well before a sedimentary rock breaks. So that's one aspect of it. The other question is how long has it gone since your last earthquake? And this is the big one. Again, what do we hear about in America? We hear about San Francisco, of course. And they always talk about the big one, the big one. Believe me, they'd rather have a dozen little ones in between than nothing and waiting for that big one. Because think of it as a valve, all right, a steam valve. It lets off the pressure. Those little cracks that the pencil was making was an attempt to let off energy that was building up in its system instead of breaking entirely. So if you have these little earthquakes, these little burps, if you would, they don't allow the pressure to build up. But if nothing happens for decades, let alone couple hundred years, There's so much energy that can get built up. And hopefully at this point, understandably, then that much worse the earthquake will be. So they actually looked into, it's funny, you're not allowed to frack in New York State anymore, I don't think at any rate. But one of the things they were looking into years ago in places like San Francisco and in a couple of cities in Japan that are really affected by this was injecting water into the fault lines to try and get them to slip more recently, just lubricate them basically. Keep it moving. Your plates are always moving. And I know it's hard to believe that after the millions and millions of years that the plates have been moving that they're not worn smooth yet. But they're really not. Like if you imagine rubbing your knuckles together and you get that as you go back and forth. All right? The plates aren't smooth somehow at those boundaries yet. There's still plenty of places for them to catch on one another, plenty of places for them to lock up. So they looked into injecting water into it to kind of help them slide by better. So again, jump back to when we were fracking and they started realizing that all this fracking water that they were injecting back into the earth was causing earthquakes. Everyone in geology was like, well, duh, we told you, we were working with that actually. How's it going? They didn't get to try it too much because the idea of telling people you're going to cause a whole bunch of small earthquakes doesn't really make them feel that much better, as it turns out, than if, we'll take our chances and wait for that one big earthquake. So I don't think they went very far with that research, but it was definitely something they were looking at. So it was no surprise when we found out that injecting the fracking water back into the earth caused some slips, some creaking and groaning there. We expected it to. At least in Ohio, that's what got it banned. I don't know what happened here, but the exact reason. But I know in Ohio it was all the earthquakes. They were like, we've never had this many earthquakes before. They thought some mad scientist was doing something here. It was just the gas company. All right, I cannot plug in and my battery is closing in, so I'm going to try and pick up my pace a little bit here. So when we talk about damage, you've got primary and you've got secondary. All right? Obviously, the ground breaks, the buildings crumble. That's primary stuff. It's horrible. It is what it is. Structural damage, landslides, that can certainly happen. Not in a city necessarily, the landslides, but other places. But secondary damage, which isn't on here, people didn't really necessarily associate it. But as soon as I mention it, you're going to be like, oh, yeah, crap. What's in the ground? We've got, in many cases, our electrical wiring. We've got our water lines. We've got our gas lines. Okay? And right now, it's the gas lines that are the problem. They get a lot of fires from earthquakes. And the problem is when those gas line breaks, as I just mentioned, the water lines break. And you can't put out the fires. That is a lot of damage. There's a video I show, and maybe I'll show it to you guys this semester, about the great earthquake in San Francisco, 1901, 1903. I forget exactly when it was. Leveled the place. And ends up that the fires, though, did way, way more damage than the earthquake itself. There's a lot more stuff built of wood back then, but even still, fire's a problem. All right, tsunamis. Changing gears again here. You may not have known how to spell it, but you've certainly heard this word before. And they're getting a little better in the media. You don't hear the word tidal wave so much. When I was growing up, they always called it a tidal wave. It has absolutely nothing to do with the tides. All right? And a tidal wave, a wave caused by the tides, isn't a thing anyhow. So it was always kind of a misnomer from the get-go. But think of this as a jacuzzi effect. All right, in a jacuzzi, you've got air jets, and they push out and they make these air bubbles. Okay, and those bubbles work their way to the surface, and they harmlessly pop. Well, imagine the same thing, but just with a giant smash, and that air comes out of all the bubble holes at once and just pushes all that water up. It's going up and over the side of your hot tub. Okay, that's what's going on with the tsunami. And the thing about it is, and this is what's so tough about them, is you can't actually tell if it's happening until it gets close to the shore. There's so many instances of ships that are out at sea. To them, it's just a normal roll. But what happens is once the word is a waveform. We haven't talked about oceanography yet, but the way waves move is sort of a circular pattern, okay, that energy moves through. And you don't notice it until that waveform hits shallow waters and it collides with the ocean floor, the shoreline, if you would. So as it travels through the open sea, it's no big deal. It's just a swell. But once the bottom of that wave hits the sand, it starts tumbling forwards. And it builds and it builds and it sucks all the water out. Maybe you've seen them on YouTube. Again, I try not to show stuff like that. But when you see the water go out for a wave, and then it just keeps going and it keeps going and it keeps going, that's not a good sign. Go very far inland if you can, okay? At any rate, there are some videos out there, and you'll see this. It's those, the hotels and condos and whatnot that are along the shorelines. They have cameras nowadays. Everybody has cameras. So there's a famous one out of Indonesia somewheres. And, stupid humans are standing there looking at it. I have to admit I probably would have been too. Where's all the water going? But every animal ran. No animals were hurt, which is kind of crazy. We'll get to that in a couple minutes. But then it just kept coming in and coming in and coming in and flooding everything. Think about it if you've been lucky enough to get to the beach, all that stuff that's at shoreline, okay? Just goes. Can also be caused by an asteroid impact. Just think about if someone threw a bowling ball into a swimming pool. Okay, same idea. Doesn't matter which direction the force comes from. Not a whole lot we can do. The problem is we've got a lot of short-term things we could notice. Foreshocks. You've heard of aftershocks. Foreshocks come beforehand. And the problem is they don't always lead to an earthquake. The land might swell a little bit from, again, that pressure. But Mother Nature works in her own time frame. That could stay there for 300 years. Or it could snap the next day. Foreshocks are what we'd really like to use. The problem is again, think about a big city where we're in this situation where they have to worry about earthquakes. And it's the boy who cried wolf kind of scenario. So the geologists say, hey, we've got these foreshocks. They don't look good. I really think you got to get your people out of town, Miss Mayor, Mr. Mayor, whatever. And let's say they listen to him this time. They say, all right, I'm up for re-election. I don't want to have this on my record. We better listen to the scientists here. Evacuate everyone out of town, disrupt jobs, production, everything. Nothing happens. Well, you go a couple more weeks, there's some more little rumbles here and there. You get where I'm going with this, okay? They're not going to keep evacuating just because the scientists say the earth is rumbling. And one time, it is going to be the real one. And then what do you do then? So there's just not a whole lot. And believe me, there's big, big bucks in this. If you could solve, this is up there with like curing cancer. Well, that's still really big, but this is big. Okay? Think of the 246,000 we were just talking about in Turkey. If someone could figure out a way to do this, it'd be amazing. The best tool we have, I mentioned a minute ago, the animals. Okay? They're, there's not a good way to say it. They're just more in tune with nature than we are. Some of you, once it comes summertime, you might like to go all natural, and you're out there in your bare feet, and you're walking around, and you're like, oh, I'm in touch with nature. And yeah, definitely more so than someone with, 2 inches of rubber under their feet. But still, we've got pavement everywhere, this, that, and the other thing. It's not that the animals have, a sense that we don't have or anything like that. They're just still, more in tune. I think. That's, it's not a hard answer. But we're animals too, so, there's no reason we wouldn't have the same abilities. But honest to gosh, you look at any of these, especially the tsunamis, every animal runs away, flies away, crawls away, whatever it needs to do. That one that I was telling you about where there's the video footage over somewhere in the southeast of Asia there. Many humans lost, not a single animal. They broke their chains, they ran. Crazy. So they knew. But you can't evacuate a city on that, So. All right, there is a lab that goes along with this. You guys right now might not get that this week. We got other stuff going on, but you will do an earthquake lab at some point. And it's kind of cool. It's online, and you get to work with real earthquake data. And what it does is kind of like what they do with cell phones now when they try to ping you. You're a hiker lost in the woods. They try to triangulate. You use 3 points to find a fourth, a point in the middle. All right, and they'll ping you from different towers and see how long it takes to bounce back, and that's how far away from that tower you are. I don't know if you know how that works, but that's how that works. And so you draw a circle around that tower, and then they do it with a couple other towers. At some point, those circles are all going to intersect, ideally at one point. And that's where you, or in this case, the earthquake was. They measure those P waves, and they say, okay, that had a travel time of this far away. Actually, they measure the difference between the P and the S, and that tells you how far away in a numerical value, 300 miles, let's say. But you don't know if it's north or south or east. You don't know that. So that's why you have to draw 3 circles. So you're going to have a circle that indicates 300 miles. Let's say another seismograph says that the earthquake was 150 miles away. So you have a circle around that seismograph, a smaller circle, because it's only 150 miles instead of 300. And then a third tower. And where all 3 of those, again, as I said, intersect, that should be where the earthquake is. It's pretty neat. Nowadays, of course, we have cities, and towns relaying with their cell phones and let alone news media that, hey, we just had an earthquake. But back in the day, this was a little more necessary. And it's still necessary to find an exact spot. And you don't need to see that, but that's the little curve you'll use. There's an example of what I was just talking about. So each dot is a seismograph, and then the circle around it indicates the radius. Bigger circle, longer distance. Smaller circle, shorter distance. All right, and since we're seriously low on battery life, I'm going to kind of skip through this stuff. Here we go. It was 2011 was the New York one. It was outside of Albany. 2.2 miles, 13.3. But what we actually felt, funny thing is we felt the top one, because this happened, I'm in Rome in the afternoons. Or I was in Rome in the afternoons. So we actually felt the one from Richmond, Virginia. Everybody slept through the Albany one. So funny thing about this is that who am I? What do I know? But I believe in that whole butterfly effect thing, right? Something happens here, it's going to affect somewhere else, it's going to affect somewhere else. I noticed anecdotally over the years that when you have one earthquake, you tend to have a few more in other places. So I asked my teacher, and he's like, oh, there's no relatable evidence between that, and so on and so forth. And it didn't blow me off, but just like, no, you're wrong. Okay. But here we see over and over and over again that we talked about the one in Turkey, and there was, an earthquake in Buffalo. There were 100 more in places you didn't even hear about. And that's probably where I'm just, there's a word for it, where you notice a pattern that isn't really there. Your brain makes a pattern out of stuff. There's a word for it in psychology. But I still think there's something to it. You can't help but, again, we had one in Richmond, we had one in Albany. You got to look where the oddities are. You don't usually have them in Albany, so let's study that one. There's a research project in there somewhere. But no, it is true. I've told you before, I do the natural disasters map with my online students. And online students, you should be recording these Turkey earthquakes and this Buffalo one, by the way, at least spring semester of 2023. What was I saying? What did I say right before I talked to my computer? At least one of you was listening, I'm sure. None of you, really. You got to look at the oddities. So their natural disaster map. I tell the students to keep up on it. It's current events. Doesn't happen every day, but you look for the big stuff that makes the news, right? And there's always a couple students that, I'll do it the last week. We all have those projects we try to do the last week. So they go on to the Geologic Survey's websites for earthquakes, and they try to pull up earthquakes that happened for the last 3 months, and they get a list of thousands of them. Okay? These rumbles happen all the time. The thing is that most of them are where nobody is. It doesn't make the news cycle because nobody cares. Okay? It's in the middle of Iowa where nobody lives, or those 8 people there, and you know what? They already knew about it. That's not going to make the news cycle. So these things happen all the time. They're little ones. They're in the background, but it's 2.2 or whatever we just said. That is a little one. Okay? Now, yeah, if you were in Albany and your house happened to be right at that epicenter, that focus, you felt it more than we did in Utica, don't get me wrong. But it makes New York State news, if that. Regional news, probably. But it doesn't make the national news. So my point is, and me going back to talking about the butterfly effect, and there's got to be some connection here. There's so much background earthquakes going on all the time that it probably isn't related. But I don't know. I just can't, like I said, 20 years, 30 years later, it's still in my mind. Yeah, so here's an example. This is 1 week in August of 2011, and all those dots, just 1 week. It's hard to see, but trust me, there's like 3 dozen dots on there, 4 dozen dots. Those are all earthquakes, okay? So they're there all the time. So back to the current events, okay? Hopefully yesterday's earthquake and secondary earthquake in Turkey won't be anywhere near as devastating as the first one. They are calling it an aftershock, by the way. And that's, we've always wondered, those of us in geology who aren't seismologists, where do you draw the limit time-wise or magnitude-wise? that it's not its own earthquake, But they're calling it an aftershock at any rate, which means it's the same seam. They think it's related to the last one, and it's still just sort of settling into place. They've probably had a half a dozen in between then and now that were even smaller that probably just didn't get picked up, by the news. But so hopefully it won't be anywhere near as disastrous. All right, and so that ends our news interruption there with earthquakes. Okay, when we come back to class, we will get back to our normally scheduled lecture.